Good afternoon. Today I'll be talking about quaternion. So today I'll be giving the origin of quaternion, some of the brief history of the rural mathematical history, operation and rotation of quaternions. The discovery of quaternion was very important to the development of abstract algebra. Quaternion is used to represent 3D reflection and rotation in different movies and graphics. Almost in the 3D dimensional space in computer graphics and navigation systems, the main reason why quaternion was developed and is useful. It's using other aspects of life such as control theory, signal process, altitude control, physics, optical mechanics, and numerous other stuff. That's a little brief introduction about what is quaternion used for and applicable in life. Now let's talk about the structure of quaternion. Quaternion basically is an extension of complex number, in which complex number has a plus b with a real number and an imaginary. A quaternion on the other hand has one real number, the imaginary parts, and those imaginary parts are I, j, and k, and which each represent an axis of rotation. And each I, j, and k each represent square root of -1, just like the imaginary I. Quaternion are associative but not commutative, which simply means a non-abelian. Just in reference, just in case when we're talking about that. It consists of multiplicative inverse and conjugate. The letters that are used to represent quaternion is H and Q. H was named after Hamilton for his invention, and quaternion has an order of 8. Let's talk a little bit about the structure. So we're still talking about quaternion, the structure, the history, the brief operation behind it. Quaternion is a non-abelian group, meaning that in a clockwise rotation, if you take j times k, which is your r, and you go in reverse, you go counterclockwise, k times j will get you a negative r, because in the direction you're rotating positive and going back get you negative. So you cannot reverse the operation, as I show you in the table. If you take 1 times 1, you get 1, r times r get you -1, but if you take r times j, you get k, and you go j times r will get you a negative j. Let's talk about the history behind quaternion. It started with Benjamin Rodriguez, who was born in 1795 in Bordeaux, France. Benjamin was a French banker, a mathematician, and social reformer. In 1815, he awarded a doctorate in mathematics by the University of Paris, and his dissertation, which is now called the Rodriguez formula. In 1825, he published work on social reform and banking, which caused the other mathematical work to be known by the mathematical community, because they felt that he wasn't really a true mathematician. In 1840, however, Transforming Group, which led to the discovery, he published Transforming Group, which led to the discovery of quaternion by William Hamilton later on. But this is prior to William Hamilton inventing and discovering it. William Warren Hamilton was born August 4, 1805 in Dublin, Ireland, considered prodigy. In 1822, he discovered an important error in late-place theory, celestial mechanics. He caught the art of Royal Astronomer at the Trinity College. Then in 1823, he entered Trinity College at Dublin. 4 years later, he was appointed professor of astronomy and then eventually astronomer of Royal for Ireland, in which he overtook the position for the person who discovered him in 1823. In 1827, he produced his first work, Theory of System of Array over Optics, the Theory of Optics. Well, in 1833, after reading a paper about complex numbers, he became very obsessed about algebraic couplets. Hamilton's graduate work consists of a complex number in which he comes to a plus b and consists of vectors, which he coined the phrase. The rotation discovered by the algebraic couplets. Still obsessed, and he was so obsessed in hoping to develop a 3-dimensional algebraic complex number. Hamilton was unsuccessful because he couldn't figure out how to multiply or allow division. so he was unable to do that part, which he spent his 7 years trying to figure it out. But on October 16, 1843, while walking on Royal Canyon in Dublin, he realized it required 3 parts. Imagine part, which is I, J, and K, right in this I. He discovered the continuum in 1843 and spent the next 20 years trying to apply continuum to problems in applied mathematics. His study led to the discovery of Hamilton mechanics, which was called Newtonian mechanics, but was changed to Hamilton after his discovery of continuum, which is vital to the field of mechanics and electromagnetic. He died September 2nd, 1865, same place he was born, Dublin, Ireland. Included a picture down to show you his lifespan from 1805 to 1886, in which they have a stamp after him. After Hamilton, right, the 2 other people continued his work. It was Peter Triggs and Benjamin Pierce, who continued to advocate the use of continuum after Hamilton's death in 1865. Well, they were trying to get it to be used in physics, geometry, and by using vector, which describe entirely through continuum. Another 2 that was continued using this process in 1880 was Joshua Ward and Oliver Hebser, who began to display continuum to vector analysis. So a little bit brief history about continuum, who invented it, and how it was carried out. Now let's talk about the rotation. Rotation. Well, we talked at the beginning. We said continuum was used for 3D and 4D rotation, right? But what does that mean? That means that you're taking a specific vector and rotating at an angle. Continuum represents rotation by the axis in the imaginary part. So Q is used to compute the rotation, which the unit vector by a certain angle. So for example, V equals xi plus is a vector, and this vector can be rotated by the angle using a linear operation, in which Q is cosine theta over 2, which is the angle, and V the vector times sine theta over 2. And if you multiply those 2 times the conjugate, the direction and the length of the vector will not be affected, but you have the rotation that you need. Taking a follow, I provide some friend where Q is equal to S V, the coordinate, which S and V will both represent S is cosine and V is the vector sine theta. Okay. So if you multiply those 2, you see at the bottom as I did, you will find out that the vector is not changed, the length or the direction is not altered. Where you gotta rotate the vector. Since all continuum are hyper multiplying by another, they will yield a third continuum. So continuum operation is interpreted as a point or a vector in which a rotation with respect to a fixed coordinate is framed. Continuum represents 2 things in rotation: the axis in which the rotation is occurring and the angle in which the rotation will occur. Any continuum can be formed a vector coordinate in which the rotation by the axis Q through an angle. So now we talk about the rotation. So now let's talk about another way to rotate, which is called Pauling spin matrix, which is a zebra spin in 3-dimensional spherical direction. Pauling matrix is denoted by a 2x2 matrix in which any continuum can be rewritten. Pauling spin matrix is isomorphic to a continuum, so that's what makes it easier to rewriting in a Pauling spin matrix and doing the rotation, because we visually see the 2x2 matrix and it's easier to rotate. Okay, I'll give you an example of continuum. This is the continuum, which H equals AU, which is the identity matrix, which is basically a real number, B times R, which and the 3 R, J, and K represent the 3 continuums. And if you notice that the Pauling matrix and the continuum matrix are isomorphic to one another. Okay. Pauling matrix. Continuum can be expressed in a 2x2 matrix, which is written as a linear combination. So basically, any Pauling continuum matrix can be written into a Pauling matrix. And that's my conclusion for continuum. Here's 3 questions I have for you. What is used to identify a continuum group? Okay. What 3 letters did Hamilton used, and what do the squares of each represent? What is continuum used for? And those are the questions I have for you. Thank you for your time. I appreciate you listening. Have a wonderful day.